Hey guys, let's talk about Newton's laws of motion. So, Isaac Newton, you don't have to remember any of this. I just like to bring up a little bit of background about the scientists that we talk about. He was born in 1643 in England. He was a very prolific scientist, especially for his time. He mainly studied physics and mathematics, and he did a lot of really amazing things for the amount of technology that he had to deal with. So um, during his lifetime, there was something called the bubonic plague going around. Can't imagine what that was like. So people had to periodically go into isolation so that they could survive. It was a very deadly kind of illness. So he spent a lot of time in quarantine, like we have, and he did a few things while he was there. He invented calculus, which is an amazing and complicated mathematical tool. He solved the binomial theorem. He was able to study the properties of light, and he split light into the different colors of the rainbow. And he also began his work on mechanics, and that's what we're going to talk about today. He developed 3 laws of motion. So, I know you've talked about these before, particularly in middle school. I'm probably going to talk about them slightly differently because the way they tend to be stated will contribute to people developing misconceptions about the laws of motion. And I want to make sure that you guys don't develop or maintain any misconceptions. All right, so Newton's first law says first that an object at rest tends to stay at rest. We've all seen like that magic trick where you have a place setting and a tablecloth underneath, and somebody whips the tablecloth out from underneath, and the dishes all stay there, hopefully. That is an example of objects that are at rest, mostly staying at rest. An object in motion tends to stay in motion. And it has to be moving at a constant speed and in a straight line. This was not obvious to people at this time. Beforehand, the Aristotelian view. So Aristotle, you probably heard about him, was a very influential philosopher in Greek times, and a lot of his views about how nature works were adopted by people and widely held, but he was very often not right. So Newton's idea that an object that's in motion will tend to stay in motion was not not widely held at the time. It might seem like, well, duh, that's how things work now, but it's not. It wasn't at the time. So if you imagine this ball is rolling down the incline, yes, there's gravity acting on it to get it to move. And then it gets to the horizontal part. Let's imagine that there is no friction to slow it down. What would happen to the ball? Well, Newton postulated that it would continue moving forever unless something came along and applied a force to it. So if there was no force acting on the ball, then it would move forever at a constant speed and in a straight line. And then the third part of Newton's first law is that unless these are acted on by an unbalanced force. So an object in motion tends to stay in motion, moving at a constant speed in a straight line. An object at rest tends to stay at rest unless they're acted upon by an unbalanced force. So in other words, forces are required in order to change the motion of an object. This is the big takeaway from Newton's first law. If there aren't any forces, or if there isn't an unbalanced force acting on an object, then it won't accelerate. It will just keep doing what it's already doing. All right. This is also known as the law of inertia. So some people will just call it that. Instead of Newton's first law, they call it the law of inertia. Inertia is the tendency of an object to resist changes in its motion. Newton's second law relates the net force, the mass, and the acceleration of an object. We've already talked about Newton's second law. We just haven't called it that. Force and acceleration are directly proportional. The more force you apply to an object, the more it will accelerate. When we say directly proportional, that means that the bigger one is, the other one also has to get bigger. Or if one gets smaller, the other one has to also get smaller. So this is how I remember directly proportional. They do the same things. So twice as much force acting on an object will cause twice as much acceleration. And then we also have the relationship between mass and acceleration. So mass resists acceleration. The more mass something has, the more it will resist accelerating. So that means that mass and acceleration are inversely proportional. If mass gets bigger, acceleration will be smaller. If mass gets smaller, acceleration will be bigger if we're talking about the same amount of force. So inversely proportional means they do the opposite. So imagine a certain amount of force is applied to a brick, it accelerates a certain amount. Then if you apply the same amount of force to twice as much brick, then you get half the acceleration. If you have 3 bricks, you get a third of the acceleration. That's inversely proportional. Now, if we put these two ideas together, we get the equation for Newton's second law. You've already seen this. It's most commonly written as force equals mass times acceleration. I usually introduce it like this. Acceleration is equal to net force divided by mass, because that makes that relationship that we were just talking about a little bit more obvious. Bigger net forces lead to more acceleration. Bigger masses lead to smaller accelerations. All right, but it's commonly known as this, F equals ma. It's the exact same equation. So remember that force is always measured in newtons, mass is measured in kilograms, and the acceleration is in meters per second squared, meters per second per second. These are the units that you need to use in this equation. So if you have mass in something other than kilograms, you'll have to convert it to kilograms. And also, this force is a net force. It has to be a net force. If you have more than one force acting on an object, then you need to determine the net force before you can use it in the equation. All right, so let's do a sample calculation. We've got a race car. It has a mass of 1,000 kilograms. There's a net force of 2,000 newtons acting on it. What acceleration does that cause? Notice this, I gave you net force, but let's imagine that the net force comes from, there's, let's say 3,000 newtons from the engine. The engine pushes it forward with 3,000 newtons, but there's air resistance and friction together that are acting in the opposite direction. There's 1,000 newtons of those. So the net of those forces together is 2,000 newtons. And that's the net force that we have to use in the equation. So the mass is 1,000. The net force is 2,000. Pause the video, take a few seconds and figure out what the acceleration should be. Plug it into the equation. You may be able to do it in your head. These numbers are easy to divide in your head if you are able. If not, that's okay, use a calculator. All right, so we'll plug those numbers in. The net force is 2,000 newtons, and the mass is 1,000 kilograms. And when we divide those, we get 2 meters per second squared. You could have units of newtons per kilogram. That's not the best way to write units, but if you've forgotten the units for your acceleration, you can take what you see in the problem, n divided by kg. It means the same thing as meters per second squared, but this is the better way to write it. It means more. But this newtons per kilogram is not wrong. Okay. So Newton's third law. I have a thing about Newton's third law, so please bear with me. I'm going to probably say it in a way that's different from what you're used to, because the typical way of stating Newton's third law leads to a lot of misconceptions. So let's just bring that right up. Newton's third law tends to be stated as every action has an equal and opposite reaction. And that's not the best way to state it, because what I tend to hear or see people do is misinterpret that by thinking that, let's say, I push on a book. That's the action. Okay, we can agree on that. I push on the book, and as a result of my push, the book moves forward or accelerates forward. That's what people tend to think of as the reaction, but it is not actually the reaction that is part of Newton's third law. So let's talk about that. I'm going to state it differently than you're probably used to. Every interaction between two forces, and every interaction between two objects involves two forces. Each object pushes on the other object with a force that is equal in size and opposite in direction. At the bottom, we've got a table with a book resting on it. The book pushes down on the table, and as a result, at the exact same time, the table also pushes up on the book. They happen together at the exact same time. They're simultaneous. They don't actually happen one because of the other. It's not really a cause and effect. They happen at the exact same time. You cannot have one without the other. And we need to talk about Newton's third law, force pairs. So every force has a pair force that occurs at the exact same time. And that would be the book, for this particular picture. The book pushes down on the table, and the table pushes up on the book. That is a Newton's third law force pair. These two forces are equal in size, and they're opposite in direction. And a Newton's third law force pair always acts on different objects. So notice the book pushes on the table. The other force is the table pushing up on the book. Always happening to two different objects. They each impart a force on the other. So let's practice identifying Newton's third law force pairs. We have a swimmer, and she is just about to push off of the wall so that she can accelerate forward and swim to the other side. She has her feet on the wall, and she's about to push on the wall. If she pushes on the wall, what is the reaction force that occurs at the exact same time? Think about that for a sec. Maybe pause the video if you need to figure it out. All right. The reaction force, or the Newton's third law force pair, I prefer to call it, is the wall pushing on the swimmer. So it is actually the force of the wall pushing the swimmer forward that makes her accelerate. Yes, it's due to her muscles exerting a force onto the wall, but the wall pushes her forward. She pushes the wall back, the wall pushes her forward. That's a Newton's third law force pair. Here's another one. A baseball player swings his bat, and the bat hits the ball. So the bat pushes on the ball. Oftentimes, people will want to say that Newton's third law says that the ball accelerates as a result. And yes, that is true that it happens, but it is not actually a result of Newton's third law. That would be Newton's second law. Newton's third law states that at the exact same time that the bat pushes on the ball pushes on the bat. Notice how we have a pattern here. Every Newton's third law force pair occurs between two objects. In this instance, it's the bat and the ball. The bat pushes on the ball pushes on the bat. So we can always say you've got two objects. Let's say object A, object B. Object A pushes on object B, and object B pushes on object A. That's a Newton's third law force pair. All right, so to summarize, I put these in like really basic language. Newton's first law says objects keep doing what they're doing unless an unbalanced force acts on them. Newton's second law is that relationship between force, mass, and acceleration. And Newton's third law says that every time two objects touch or push on each other, they apply a force on each other. These forces are equal in size and opposite in direction. And that is it.